the discovery of a new moon orbiting the ice giant. Uranus represents one of the most significant milestones in modern planetary science, underscoring the revolutionary impact of the James Webb Space Telescope, JWST. This celestial find was not merely a stroke of luck but the culmination of sophisticated observational techniques and the unparalleled sensitivity of JWST's infrared instruments. For decades, the Uranian system was thought to be well mapped. Yet this discovery proves that even within our own solar system, there are profound mysteries hidden in plain sight. By peering through the vast distances of the outer solar system, Webb has effectively reopened the book on a planet that hasn't seen a dedicated visitor since the Voyager 2 flyby in 1986. To understand the magnitude of this find, one must first appreciate the extreme difficulty of observing the Uranian environment. Located nearly 2 billion miles from the Sun, Uranus receives very little sunlight, making its smaller satellites incredibly faint and difficult to detect against the glare of the planet itself. Previous ground-based telescopes, and even the Hubble Space Telescope, faced significant limitations in resolution and light-gathering power when tasked with finding objects only a few kilometers in diameter. The new moon, which had remained undetected for centuries, was finally brought into focus by Webb's ability to capture long infrared light that bypasses many of the visual obstructions found in the outer solar system. The James Webb Space Telescope's near-infrared camera NIRCam was the primary tool used in this breakthrough. Unlike traditional optical telescopes, NIRCam can detect the faint heat signatures emitted by cold, icy bodies. While these moons do not glow in the visible spectrum, they retain enough thermal energy to stand out against the absolute zero of deep space when viewed through Webb's gold-plated mirrors. This specific wavelength advantage allowed astronomers to filter out the overwhelming reflections from Uranus's thick hydrogen-helium atmosphere, revealing the tiny pinprick of light that would eventually be confirmed as a new natural satellite. The initial detection occurred during a series of deep-field observations intended to study the chemical composition of Uranus's rings. As the data was processed, researchers noticed a consistent anomaly, a faint object that appeared to move in a stable, repetitive pattern relative to the planet's center of mass. Unlike background stars, which remain stationary, or cosmic rays, which appear as random streaks, this object followed a distinct arc. This sparked an immediate investigation, as the mathematical probability of a random asteroid appearing in multiple high-resolution frames at those specific coordinates was statistically improbable. Verifying the discovery required a rigorous multi-step process involving complex orbital mechanics. Astronomers had to ensure that the object was truly gravitationally bound to Uranus and not a trans-Neptunian object, TNO, simply passing through the field of view. By analyzing the object's velocity and the curvature of its path, scientists were able to calculate its orbital period. This data confirmed that the object was locked in a permanent dance with the ice giant, officially elevating it from a candidate to a confirmed moon, marking the first time in over 20 years that a new satellite has been added to the Uranian tally. Initial estimates of the moon's physical characteristics suggest a body of modest proportions, likely measuring between 10 to 20 kilometers in diameter. In the context of the solar system, this makes it an irregular moon, a category of satellites that are typically small, have eccentric orbits, and are often tilted at high angles relative to the planet's equator. Because of its small size, it likely lacks the internal heat necessary for geological activity, meaning its surface is probably a pristine, cratered record of the early solar system's history. This makes it a time capsule of sorts, preserving materials that have remained largely unchanged for billions of years. The orbital trajectory of this new moon provides vital clues about its origin story. Most of Uranus's larger moons, like Ariel and Umbriel, likely formed from the same disk of gas and dust that created the planet itself. However, the irregular orbit of this new find suggests it was a captured object at some point in the distant past. This moon was likely a wandering comet or asteroid from the Kuiper belt that ventured too close to Uranus's gravitational well. The planet's immense gravity snagged the traveler, slowing it down and forcing it into a permanent orbiter, violent and chaotic, process that defines much of the outer solar system's evolution. This discovery also sheds light on the complex relationship between moons and its unique ring system. Uranus possesses 13 known rings, which are much darker and thinner than those of Saturn. Small moons, often called shepherd moons, play a critical role in maintaining these rings by using their gravity to herd ring particles back into place. Scientists are now investigating whether this new moon exerts any gravitational influence on the outermost rings. Even a tiny satellite can create waves or gaps in ring structures, and understanding these interactions helps researchers model the long-term stability of the entire Uranian environment. Furthermore, the find highlights the sheer efficiency of the JWST mission. While Webb was designed primarily to look at the first stars and galaxies of the universe, its secondary mission of planetary science is proving to be just as revolutionary. The fact that it can pivot from observing galaxies billions of light years away to finding tiny rocks in our own cosmic backyard demonstrates versatile range that no other observatory in history has possessed. This dual-purpose capability is providing a more holistic view of the universe, linking the physics of the very distant past to the current state of our local planetary neighborhood. The scientific community is now faced with the task of naming this new celestial body. Following the long-standing tradition established for Uranus, the name will likely be drawn from the works of William Shakespeare or Alexander Pope. Previous moons have been named after characters like Desdemona, Juliet, and Cordelia. This cultural link between classical literature and cutting-edge science adds a layer of human history to the discovery, reminding us that our exploration of the stars is a continuation of the same curiosity that has driven artists and thinkers for centuries. Beyond the name, the composition of the moon is the next great mystery to solve. Using spectroscopy, Webb can analyze the light reflecting off the moon's surface to determine what it is made of. Astronomers expect to find a mixture of water, ice, carbon dioxide ice, and dark carbon-rich organic compounds, known as. If the moon contains high amounts of volatile ices, it would confirm its origin in the far reaches of the solar system, where temperatures are low enough for such materials to remain solid. This data will help map the distribution of chemicals across the solar system's frost line. The discovery also serves as a powerful argument for a dedicated flagship mission to Uranus. While Webb is a magnificent tool, it is a remote observer. To truly understand the dynamics of this new moon and its parent planet, scientists believe we need an orbiter, Uranus orbiter and probe, similar to the Cassini mission at Saturn. This new moon adds a fresh target of interest for such a mission, providing more justification for space agencies, like NASA and the ESA, to prioritize a journey to the ice giants in the 2030s or 2040s. From a broader perspective, the discovery challenges the notion that the solar system is a completed map. It reinforces the idea that planetary systems are dynamic and crowded places. If a planet as large as Uranus can still hide a moon from our best telescopes for decades, it stands to reason that Neptune, and even the hypothetical planet 9, may hold similar secrets. This discovery keeps the spirit of exploration alive, proving that we are still in the age of discovery, and that our understanding of our own home is still evolving. Moreover, the data gathered during this discovery is being shared across global networks, allowing for collaborative science. Amateur astronomers and university researchers can use the orbital coordinates provided by NASA to attempt their own observations, though the moon's extreme faintness makes it a challenge for all but the largest professional rigs. This open-source approach to space science ensures that the discovery is vetted by the best minds in the field, leading to more accurate models of the moon's mass, density, and eventual fate. One of the more technical aspects of the discovery involves the wobble the moon might induce on Uranus's other small satellites. By studying these tiny gravitational perturbations, physicists can weigh the moon without ever touching it. Knowing the mass is essential for determining if the moon is a solid rock or a rubble pile, a loose collection of boulders held together by gravity. Rubble pile moons are common among captured asteroids, and confirming this would tell us a great deal about the structural integrity of objects in the Kuiper belt. The discovery also has implications for the safety of future spacecraft. As we plan missions to the outer planets, knowing the exact location of every moon and ring fragment is vital for navigation. A small, undetected moon could pose a collision risk, or create a gravity well that alters a probe's trajectory. By mapping these satellites now, Webb is effectively acting as a cosmic scout, clearing the path for the next generation of explorers who will one day sail through the Uranian system. The timing of this discovery is also notable, as it coincides with a renewed global interest in ice giant science. For years, the focus was primarily on Mars and the Moon. However, as we discover thousands of exoplanets around other stars, we've realized that mini-Neptunes and ice giants are actually the most common types of planets in the galaxy. By studying Uranus and its new moon, we are actually learning about the most frequent planetary configurations in the universe, making our local research relevant on a galactic scale. There is also the element of public inspiration. Whenever a new world is discovered, it captures the public imagination in a way that complex equations cannot. It reminds us that there is still uncharted territory out there. For students and aspiring scientists, this discovery is a call to action, demonstrating that the tools of the future are now available and that there are still plenty of things left to find for those who know where and how to look. Looking forward, the next steps involve long-term monitoring. Because the moon is so far away, its orbit might be influenced by the sun's gravity, in a process known as the Kozai mechanism. This could cause the moon's orbit to tilt or stretch over thousands of years, eventually leading it to crash into Uranus, or be flung back out into space. Observing these changes, even incrementally, provides a real-time look at orbital evolution that usually takes millions of years to unfold, giving us a laboratory for celestial mechanics. Uranus occupies a unique and often misunderstood position within our solar system's hierarchy. Situated approximately 1.9 billion miles from the Sun, it exists in a realm of extreme cold and permanent twilight. This distance means that sunlight reaching the planet is roughly 400 times fainter than what we experience on Earth. For astronomers, this lack of illumination creates a significant visibility gap, where small objects like the newly discovered moon remain shrouded in darkness, requiring specialized infrared equipment to detect the heat signatures they emit against the freezing void. Unlike the gas giants, Jupiter and Saturn, which are composed mostly of hydrogen and helium, Uranus is classified as an ice giant. This distinction is crucial because it implies that the bulk of the planet's mass consists of a hot, dense fluid of icy methane and ammonia above a small rocky core. This internal composition affects the planet's gravitational field, which in turn dictates how moons are captured and maintained in orbit. The discovery of a new moon provides a fresh data point for geophysicists trying to model the gravitational influence of such a massive, fluid-rich body. The most striking feature of Uranus is its extreme axial tilt of 98 degrees. While most planets spin like tops relative to the plane of the solar system, Uranus essentially rolls on its side. This orientation creates a bizarre seasonal cycle, where the poles experience 42 years of continuous sunlight, followed by 42 years of darkness. This tilt also affects the orbital planes of its moons. Most of the primary satellites orbit around the planet's equator, meaning they also travel vertically relative to the rest of the solar system, creating a complex three-dimensional puzzle for telescopes trying to track them. Much of our foundational knowledge of the Uranian moons comes from a single event, the Voyager flyby in January 1986. During this brief encounter, the spacecraft transformed our understanding of the system, discovering 10 new moons and 2 new rings in just a matter of days. However, because it was a flyby and not an orbital mission, Voyager could only capture a snapshot in time. Many smaller, more distant moons were likely missed because the spacecraft wasn't positioned to see them, leaving a blind spot in our maps that the James Webb Space Telescope is finally beginning to fill. Before this latest discovery, the 27 known moons of Uranus were generally divided into 3 distinct groups: the 13 inner moons, the 5 major moons, and the 9 irregular moons. The inner moons are small, dark bodies that are intimately connected to the planet's ring system. The 5 major moons Miranda, Ariel, Umbriel, Titania, and Oberon are large enough to have reached hydrostatic equilibrium, meaning they are spherical. The newly discovered moon likely falls into the third category, the irregulars, which are characterized by distant, eccentric orbits. The 5 major moons of Uranus are worlds unto themselves, each with unique geological histories. Titania and Oberon, the largest of the group, show evidence of ancient tectonic activity and cratering. Understanding these large bodies is essential because their gravity dominates the system. Any new, smaller moon discovered in their vicinity must exist in a gravitational sweet spot, where it isn't pulled into a collision course with these giants or ejected from the system entirely. Among the existing satellites, Miranda is perhaps the most famous due to its Frankenstein appearance, a jumbled surface of giant canyons, ridged plains, and the highest cliff in the solar system. Verona Rupes Miranda's chaotic geology suggests a history of massive impacts or intense tidal heating. The discovery of additional small moons helps scientists reconstruct the orbital history of the entire system, potentially explaining why moons like Miranda underwent such violent transformations while others remained relatively placid. The 13 inner moons of Uranus, such as Puck and Mab, are small, grayish bodies that are deeply embedded within the planet's rings. These moons are often called shepherd moons because their gravity keeps the ring particles confined to narrow bands. Finding a new moon in the vicinity of Uranus allows researchers to check if there are additional, undiscovered rings, or if this new body is acting as a guardian for a previously invisible dusty structure. Irregular moons, the category this new discovery likely joins, are fascinating because they do not follow the neat, circular paths of the major satellites. Instead, they often have highly elliptical orbits, and can even orbit in a retrograde direction, opposite to the planet's rotation. These moons are essentially foreigners to the system, having been captured by Uranus's gravity long after the planet formed. Each new irregular moon discovered is a clue to the population of asteroids that once swarmed the outer solar system. The process by which a planet like Uranus captures a moon is a masterpiece of celestial mechanics. A passing object must lose just enough energy, either through a collision with an existing moon, or through a gravitational braking maneuver, involving the planet and the sun to fall into a permanent orbit. Studying the orbit of this new moon allows mathematicians to run backwards simulations to see where in the solar system this object might have originated, potentially linking it to the Kuiper belt. One reason Uranus's moons are so hard to find is their albedo, or reflectivity. Most of these small bodies are as dark as charcoal. They are coated in organic compounds that have been processed by space radiation over billions of years, turning them into dark, reddish-black rocks. This low reflectivity makes them nearly invisible to traditional optical telescopes, which is why the James Webb Telescope's infrared sensors, which detect heat rather than reflected light, were the key to this breakthrough. When we look at the moon counts of Jupiter 95 and Saturn 146, Uranus's count of 28, including the new find, seems small. However, this is likely a result of observation bias rather than a lack of moons. Because Uranus is so much further away, we can only see the tip of the iceberg. Astronomers estimate that there could be dozens, if not hundreds, of tiny moons at Uranus waiting to be found as our technology improves, bridging the gap between our understanding of the different giant planets. The Uranian moons are thought to be composed of roughly 50% water ice and 50% rock. This ratio is a vital indicator of the conditions in the solar nebula when these objects formed. By adding a new moon to the catalog, scientists can perform comparative spectroscopy to see if the new moon's chemical signature matches the local moon's, or if it looks more like a comet from the deep outer reaches, providing a map of chemical distribution. In the early solar system, the Uranian system is known for being dynamically crowded. The inner moons are so close to one another that their orbits are technically unstable over millions of years. This means the system is constantly evolving, with moons occasionally colliding or breaking apart. A new discovery adds a new variable to these stability models. Scientists must now calculate whether this new moon is a stable member of the family or a temporary resident on its way to a cosmic collision. The tradition of naming Uranian moons after characters from Shakespeare and Alexander Pope is more than just a quirky habit. It provides a structured way to categorize the system. For example, the inner moons are often named after characters from A Midsummer Night's Dream or The Tempest. As this new moon is categorized, its name will likely reflect its position in the system, continuing a 170-year-old tradition that connects the height of English literature with the cutting edge of space exploration. Even at the distance of Uranus, the sun plays a role in the evolution of moons. Solar wind and ultraviolet radiation slowly garden the surfaces of these moons, altering their chemistry. For a small, newly discovered moon, this radiation can actually change its orbit over eons through a process called the Yarkovsky effect. Detecting these tiny bodies allows us to study how light itself can act as a subtle but persistent force in the shaping of planetary systems. The Uranian system serves as a perfect laboratory for studying three-body problems and orbital resonances. Many of the moons are locked in mathematical ratios. For example, one moon might orbit exactly twice for every one orbit of its neighbor. These resonances prevent collisions and keep the system in balance. Astronomers are eager to see if the new moon is part of such a resonance, which would explain how such a small object has survived so long without being consumed by the planet. Uranus and Neptune remain the least explored planets in our solar system. While we have sent multiple orbiters to Jupiter and Saturn, we have only ever passed by Uranus. This lack of data means that every new moon found by the Webb telescope is a major event. It fills in the gaps of our knowledge and builds the case for why we need to send a dedicated probe to these distant, turquoise worlds to see what else might be hiding in the dark. While Webb made the discovery, the follow-up is a global effort. Earth-based observatories like the Keck telescope in Hawaii or the Very Large Telescope VLT in Chile are now being used to verify the coordinates. This synergy between space-based infrared technology and ground-based optical power is the modern standard for discovery, ensuring that one telescope's find is backed up by a chorus of scientific data from around the world. To understand why the discovery of a new moon around Uranus is a triumph for the James Webb Space Telescope, one must first understand the shift from visible light to infrared astronomy. Most of our historical images of the solar system were captured in the visible spectrum, the light humans can see. However, in the cold, dark reaches of the outer solar system, objects are often too dim to reflect enough sunlight for traditional cameras. The JWST operates primarily in the infrared, detecting heat signatures rather than just reflected light. This allows it to see objects that are essentially invisible to even the most powerful optical telescopes ever built. The James Webb Space Telescope was designed to solve a fundamental problem in space observation: the dimming of distant objects. Because Uranus is nearly 2 billion miles from the Sun, the light hitting its moons is incredibly weak. By focusing on the mid- and near-infrared spectrums, Webb can detect the faint thermal glow emitted by these icy bodies. Even a tiny frozen moon possesses a small amount of heat relative to the absolute zero of space. Webb's sensors are sensitive enough to pick up this heat, making the new moon stand out as a bright point against a dark background. Out at the heart of Webb's ability to find new moons is its massive 6.5-meter primary mirror, coated in a thin layer of 24-karat gold. These hexagonal segments are specifically optimized to reflect infrared light. Gold has a much higher reflectivity for infrared wavelengths than the aluminum coatings used on the Hubble Space Telescope. This increased reflectivity means that almost every photon of infrared light coming from the Uranian system is captured and funneled into the telescope's instruments, allowing for the detection of smaller and fainter satellites than ever before. The specific instrument responsible for this discovery is the near-infrared camera, or NIRCam. This camera is equipped with coronagraphs, which are specialized tools that allow astronomers to block out the overwhelming glare of a bright object, in this case the planet Uranus itself, to see the much fainter objects nearby. Without a coronagraph, the reflected light from Uranus's thick atmosphere would wash out any tiny moons in its vicinity, much like a streetlight hides the stars around it. Uranus is a challenging target because its methane-rich atmosphere is highly reflective in certain wavelengths. This creates a halo effect that can easily hide small moons or ring fragments. Webb's NIRCam uses a series of filters that specifically target wavelengths where methane absorbs light. By looking at these specific dark channels, the planet appears dimmer, while the icy surfaces of the moons, which do not contain as much methane, appear relatively brighter. This contrast enhancement was the key to isolating the new moon from the planetary noise. While visible light telescopes rely on the albedo or shininess of a moon, Webb relies on emissivity. Many small moons in the outer solar system are covered in dark, carbonaceous material that reflects almost no light. These stealth moons are nearly impossible for Hubble to see. However, because they are dark, they absorb what little sunlight they receive and re-radiate it as heat. To the James Webb Space Telescope, a dark moon is actually easier to see in infrared because it glows more intensely than a highly reflective, icy moon. One of the most impressive technical feats of the JWST is its diffraction-limited resolution. This means that the telescope is performing at the theoretical limit of what its optics can achieve. When pointed at Uranus, Webb can distinguish between two objects that are incredibly close together in the sky. This high resolution allowed astronomers to see the new moon as a distinct point of light, rather than a blurry smudge merged with the rings or the planet's edge, providing the clarity needed to calculate a precise orbit. The location of the JWST is just as important as its mirrors. Orbiting the second Lagrange point L2, 1.5 million kilometers from Earth, The telescope is in a thermally stable environment. It is shielded from the heat of the sun, the Earth, and the moon by its tennis court-sized sunshield. This stability allows for extremely long exposure times. To find a tiny moon, Webb can stare at Uranus for hours without any atmospheric distortion or temperature fluctuations, slowly building up a signal-to-noise ratio that reveals hidden celestial bodies. While NIRCam provided the initial visuals, the mid-infrared instrument MIRI allows scientists to dig deeper into the moon's composition. MIRI looks at even longer wavelengths, which can penetrate through the dust and surface layers of a moon. By combining data from NIRCam and MIRI, astronomers can determine if the new moon is a solid block of ice or a porous rubble pile. This multi-instrument approach is a unique capability of the Webb telescope that provides a holistic view of any new discovery. Major challenge in discovering a new moon is proving that the object isn't just a distant background star or galaxy. Because Uranus is moving through its orbit, Webb takes multiple images over a period of hours and days. By using a technique called dithered imaging, astronomers shift the telescope slightly between shots. When these images are stacked and compared, background stars remain in a fixed position, while any object gravitationally bound to Uranus moves with the planet. Webb's precision tracking makes this distinction definitive. The James Webb Space Telescope is so sensitive that it doesn't just see the moon, it sees the moon's impact on its environment. Astronomers are looking for wakes or spiral patterns in the nearby rings that might be caused by the new moon's gravity. These subtle structures are often only a few kilometers wide and require the extreme sensitivity of Webb's detectors to resolve. Finding these patterns acts as secondary confirmation of the moon's mass and orbital influence. The discovery often happens on a computer screen long after the telescope has finished its observation. Scientists use sophisticated algorithms to subtract the light of Uranus from the images. Because Webb's point spread function, how it renders a point of light, is so stable and well understood, researchers can digitally remove the planet's glare with incredible accuracy. This reveals the residuals, the tiny specks of light, like our new moon, that were previously buried in the data. Since the Voyager 2 flyby in 1986, we have had a gap in our high-resolution data of the Uranian satellites. Ground-based telescopes using adaptive optics have tried to fill this gap, but they struggle with Earth's atmosphere. Webb represents the first time since 1986 that we have had space-quality images of the system that surpass Voyager's capabilities. In many ways, Webb is acting as a stationary spacecraft, providing the kind of detail we usually only get from expensive planetary orbiters. Because Uranus has such an extreme tilt, one of its poles is often pointed away from Earth for decades. Webb's infrared eyes are particularly good at seeing into the shadows. While a moon might be in the night side of its orbit relative to the sun, it still emits infrared radiation. This allows Webb to track the moon through its entire orbital path, not just when it is perfectly illuminated by sunlight, providing a complete picture of its orbital mechanics. Webb is not just a camera, it is a powerful Once the new moon was located, Webb's near-infrared spectrograph, an NIRSpec, could be used to break the moon's light into a chemical fingerprint. This tells us what the moon is made of, whether it's water, ice, ammonia, or a complex organ. Knowing the composition helps determine if the moon formed with Uranus or was captured later, a question that only Webb's specific set of instruments can answer with high precision. Finding a moon requires a lot of data. Webb transmits its findings back to Earth via the deep space network at high speeds, allowing teams of scientists around the world to analyze the images, almost in real time. This rapid data turnaround is essential for target opportunity observations. If a candidate moon is spotted, astronomers can quickly schedule follow-up observations to confirm the orbit before the object moves too far or becomes obscured by the rings. Historically, our moon catalogs have been biased toward larger, brighter objects. Webb is systematically reducing this bias by being able to detect objects down to a few kilometers in size. Webb is giving us a more honest count of the satellites in the outer solar system. This is crucial for understanding the true frequency of moon formation and capture, which informs our theories about how all giant planets, including those around other stars, evolve over time. The technology that found this moon is the result of 30 years of engineering. The microshutter technology in IR-SPEC, for example, allows Webb to look at 100 objects simultaneously. While the telescope was looking for a new moon, it was likely also gathering data on dozens of other targets in the same field of view. This efficiency is what makes Webb the most productive scientific instrument ever launched into space, maximizing every second of its mission. Every discovery Webb makes at Uranus acts as a roadmap for future NASA missions. If we eventually send an orbiter to Uranus, it will use Webb's data to decide which moons are worth a close-up flyby. This new moon, despite being small, might have unique spectral features that make it a high-priority target. Webb is essentially doing the long-range reconnaissance that will ensure the success of the next 50 years of planetary exploration. The discovery began not with a single snapshot, but with a highly structured survey led by Dr. Maryam El-Mutamid from the Southwest Research Institute, SWRI, as part of the James Webb Space Telescope's Guest Observer program. The team secured a window on February 2, 2025, to conduct a deep field analysis of the Uranian system. This was a strategic hunt, specifically designed to push the boundaries of Webb's near-infrared camera and NIRCam to detect objects that previous missions, including Voyager 2, simply could not see. To pull a tiny moon out of the darkness, the team utilized 10 separate long exposure shots, each lasting approximately 40 minutes. In total, the telescope stared at Uranus for over 6 hours. This cumulative approach allowed the sensors to collect a sufficient number of photons to create a signal-to-noise ratio strong enough for detection. In the world of deep space photography, time is the ultimate currency. The longer you look, the more the universe reveals its hidden residents. During the initial processing of the raw data, a minuscule pinprick of light appeared in the frames. In a single image, such a speck could easily be dismissed as a hot pixel, a camera sensor error, or a distant background galaxy. However, because the team had 10 separate exposures, they could look for consistency. This tiny light was not static. It moved in a very specific, predictable arc that suggested it was physically traveling alongside Uranus through the void. One of the greatest obstacles in this aha moment was the overwhelming brightness of Uranus itself. Even in the infrared, the planet is a lighthouse compared to the candlelight glow of a 10-kilometer wide moon. To find S2025U1, the researchers had to use advanced PSF point spread function subtraction. This involves digitally modeling the planet's light and subtracting it from the image, effectively turning off the lighthouse so they could see the firefly dancing next to it. What convinced the team they had found a moon was the object's velocity. Every moon in the solar system must travel at a specific speed, dictated by its distance from the planet's center of mass and the planet's gravity. By measuring the displacement of the speck across the 10 frames, the scientists calculated that the object was moving exactly at the speed required for a stable orbit around Uranus. It wasn't a passing asteroid, it was a permanent member of the system. The public image released by NASA and ESA is actually a triple treatment composite, because the planet, the rings, and the moons all have vastly different brightness levels. A single standard exposure would either overexpose the planet or underexpose the moons. By blending 3 different data treatments, scientists were able to create a view where the atmospheric clouds of Uranus, the sharp lines of the rings, and the faint glimmer of S2025U1 are all visible. Simultaneously, the aha moment was intensified when the researchers mapped the new moon's position relative to known satellites. S2025U1 was found nestled in a tightly packed region between the orbits of Ophelia and Bianca. Ophelia is roughly 13 miles wide, while Bianca is an elongated moon about 40 miles long. Finding a new neighbor in this specific lunar suburbs was a surprise, as it suggested the inner system is much more crowded than previously modeled. The team used NIRCam's wideband F150W2 filter, which transmits infrared wavelengths from 1.0 to 2.4 microns. This specific range is a sweet spot for outer solar system observation, because it captures the thermal signatures of ice, while minimizing the interference from certain types of cosmic dust. Using this filter was a deliberate choice that made the discovery possible, as it highlighted the distinct spectral signature of a moon versus a background star. Before announcing the discovery, the team had to rule out ghosting, a phenomenon where light reflects internally within the telescope's optics. Because the JWST has a complex system of 18 hexagonal mirrors, it can sometimes create symmetrical artifacts. However, S2025U1 did not mirror any other bright features in the system. Its unique position and individual movement confirmed it was a physical body, rather than an optical trick. The data was captured in February, but the discovery wasn't finalized until months later. The spring and summer of 2025 was spent in a rigorous blind analysis, where different members of the team used different algorithms to see if they all arrived at the same conclusion. This peer review within the team ensures that the discovery is grounded in repeatable, verifiable mathematics before it is presented to the International Astronomical Union, IAU, closing parenthesis. By comparing the brightness of S2025U1 to its neighbors like Ophelia, the team estimated its size, assuming it has a similar albedo reflectivity to other Uranian moons. They calculated it to be just about 6 miles, 10 kilometers in diameter. This makes it the smallest moon ever detected at Uranus. To put that in perspective, you could drive across the entire moon in about 10 minutes. It is truly a mini-world. The new moon glides in a nearly perfect circular path approximately 35,000 miles, 56,000 km from the center of Uranus. This proximity to the inner ring system is scientifically significant because the orbit is so circular and aligned with the planet's equator. It is highly likely that this moon formed from the same primordial disk as the planet, rather than being a captured asteroid from outer space. For years, astronomers have noticed small wavy patterns in Uranus's inner rings that couldn't be explained by the known moons. The discovery of S2025U1 provides a possible answer. Its gravity, though weak, acts as a sculptor for the ring particles. Finding this moon allows scientists to rerun their ring simulations to see if this 6 rock is the missing piece of the puzzle that maintains the ring's sharp edges. The analysis process is essentially a high-stakes version of Spot the Difference. Researchers compare the new Webb images to historical data from Voyager 2 and ground-based telescopes, like the Magellan, by confirming that the object was not in those older images. What was too faint to be seen, they establish why this discovery belongs uniquely to the JWST era. While NIRCam found the moon, other instruments like UNnoticed were used to ensure the object wasn't a trans-Neptunian object, TNO, just passing through. A TNO would have a different chemical signature, more nitrogen or methane ice, than a Uranian moon, which is mostly water, ice, and rock. The spectroscopic data confirmed that this object shared the genetic makeup of the other Uranian satellites. The discovery involved researchers from the SETI Institute, the University of Idaho, and SWRI, utilizing a global network of supercomputers to process the JWST data. This collaboration allowed for the blinking technique rapidly, switching between images, to see what moves to be done with extreme precision, removing any human error from the identification of the faint pixel cluster. This discovery effectively bridges a 40-year gap in our exploration of Uranus. Since Voyager 2 left the system in 1986, we have relied on long-distance guesses about what was happening in the inner rings. Webb's data acts as a virtual return mission, providing the resolution and sensitivity that a 1980 probe simply couldn't carry. With the confirmation of its orbit and size, the conversation has now turned to its name, following the tradition of naming Uranian moons after characters from William Shakespeare or Alexander Pope. The team is currently reviewing literary candidates. This small moon, once just a nameless speck in a digital file, is now on its way to becoming a permanent part of our cultural and scientific heritage. Matthew Tiscareno of the SETI Institute noted that this discovery blurs the boundary between a ring system and a system of moons. The fact that S2025 U1 is so small and so close to the rings suggests that Uranus's history was incredibly chaotic. It's possible that this moon is a shard of a larger moon that was shattered by an impact millions of years ago. The aha moment of S2025 U1 is likely just the beginning. The success of this survey proves that there are likely more 5 to 10 kilometer moons hiding in the Uranian system. Webb has set a new floor for detection, and as astronomers refine their techniques, we may see the moon count of Uranus jump significantly in the coming years, further deepening our understanding of this sideways world. Confirming a new moon is a process defined by extreme scientific caution, as the discovery of a celestial body is only as strong as the data that supports its permanence. In the case of S2025 U1, the initial visual detection by the James Webb Space Telescope was merely the starting line of a grueling verification marathon. In astronomy, a single sighting is an anomaly. 2 sightings are a coincidence, but 3 or more sightings that follow a mathematically predictable path constitute a discovery. To move from a candidate to a confirmed moon, researchers had to eliminate every other possible explanation for that tiny speck of light. The verification began with the establishment of a search volume, a mathematical model of the space surrounding Uranus where a moon could realistically exist without being ejected by the planet's gravity or crashing into its surface. Astronomers used the Hill sphere calculation to determine this region. For a planet as massive as Uranus, the Hill sphere extends millions of miles. But the inner region where S2025 U1 was found is far more crowded and complex. The team had to map the new object's position against the known gravitational tides of the 27 previously identified moons. One of the primary methods used for verification is a modern version of the blink comparator technique, famously used to discover Pluto. Scientists take multiple images of the same patch of sky over several hours or days and blink between them on a computer screen. In these frames, distant stars and galaxies remain perfectly still, but an object orbiting Uranus will appear to jump from one position to the next. Because Webb's near-infrared camera, NIRCam, provides such high resolution, these jumps were not blurry smudges, but precise shifts that allowed for subpixel tracking. A major hurdle in verification is the interloper problem. The outer solar system is filled with trans-Neptunian objects, TNOs and centaurs, icy rocks that wander between the orbits of the giant planets. To prove that S2025U1 was a moon, the team had to calculate its velocity relative to Uranus. If the object were a passing TNO, its speed would be independent of Uranus's gravity. However, the data showed that the object was decelerating and accelerating in perfect synchronization with Uranus's gravitational well, proving it was captured or resident rather than a passerby. Once the team was certain the object was moving with Uranus, they began the arduous task of determining its orbital period, the time it takes to complete one full revolution around the planet. By analyzing the distance traveled between Webb snapshots, mathematicians used Kepler's third law of planetary motion to estimate the moon's year. They discovered that S2025U1 completes an orbit approximately every 17 hours. This rapid transit is characteristic of inner moons, and provided the first major clue that this was a prograde satellite, moving in the same direction as the planet's rotation. Verification is rarely a solo act. After the James Webb Space Telescope provided the high-resolution discovery images, the team looked to ground-based observatories to provide historical context. They scoured archive data from the Magellan Telescope in Chile and the Keck Observatory in Hawaii. By looking back at older images, with the new orbital coordinates in hand, they were able to find faint, previously ignored traces of the moon in older data sets. This recovery significantly bolstered the evidence for the moon's stable existence over time. Every telescope has optical ghosts, internal reflections, that can create false points of light. Webb's complex 18-segment mirror system creates a specific diffraction spike pattern. The verification team had to perform a deconvolution of the images, a mathematical process that strips away the telescope's own optical signatures to ensure the moon wasn't just a reflection of the bright planet Uranus. The fact that S2025U1 maintained its integrity across different filters and exposure times confirmed it was a physical body. A key part of the validation was measuring the moon's inclination, the angle of its orbit relative to Uranus's equator. Uranus is famous for its 98-degree tilt, and its primary moon's orbit nearly perfectly in that tilted plane. The verification data confirmed that S2025U1 also follows this extreme tilt, with an inclination error of less than 1 degree. This alignment is a smoking gun for moons that formed alongside the planet, as captured asteroids usually have much more erratic, highly tilted orbits. The science of measuring the positions of celestial bodies is known as astronomy, and for this discovery, it required precision down to the millisecond. Astronomers used background stars as anchors to measure the exact coordinates of the new moon. By using the Gaia star catalog, the most accurate map of the stars ever created, the team could plot the moon's path with enough accuracy to predict exactly where it would be 6 months or even 6 years into the future. Once the internal data was deemed bulletproof, the findings were submitted to the Minor Planet Center and the International Astronomical Union (IAU). These organizations act as the ultimate arbiters of cosmic discoveries. A team of independent scientists, who were not involved in the original study, reviewed the orbital calculations and the raw Webb data. Only after this rigorous peer review process was the object given its official provisional designation, S2025U1.2. Further verify the moon's mass and stability. Researchers analyzed how its gravity might be affecting its closest neighbors, Ophelia and Cordelia. Even a moon as small as 10 kilometers exerts a tiny tug on nearby objects. Using on-body simulations, supercomputers ran millions of scenarios to see if the proposed orbit of S2025U1 would cause the other moons to wobble. The fact that the observed system matched the mathematical predictions confirmed that the new moon was a harmonious part of the Uranian family. While the fifth paragraph focuses on the orbit, The verification also included color analysis. By looking at how the moon reflected different wavelengths of infrared light, the team confirmed that its color matched the neutral gray palette of the other inner Uranian moons. If it had been a bright red or deep blue, it might have been an atmospheric artifact or a distant galaxy. The gray signature served as a chemical confirmation that the object belonged in the Uranian neighborhood. Part of the validation process involves looking into the future. Scientists use the Lyapunov time calculation to determine if the moon's orbit is stable over millions of years. This is important because some moons are actually temporary captures that will eventually be flung out of the system. The simulations showed that S2025U1 is in a stable resonance with the planet's rings, meaning it has likely been there for billions of years and will remain there for the foreseeable future. Verifying an object this faint, estimated at a magnitude of 25 or higher, requires a deep understanding of Poisson noise, the random fluctuation of photons hitting the camera sensor. The team had to prove that the signal from the moon was statistically higher than the random noise of the background sky. Through a Monte Carlo statistical analysis, they determined there was a 99.999% probability that the object was a real, physical entity, and not a random clustering of background photons. The discovery was not limited to just one of Webb's cameras. The team used both NIRCam and the Fine Guidance Sensor (FGS) to track the object. The FGS is usually used to keep the telescope pointed steadily at a target, but its high-precision data can also be used to detect moving objects. Having two independent instruments on the same telescope see the same object at the same time provided an extra layer of hardware verification. That is rare in deep space discovery. In the official record, every moon must have a discovery epoch, the exact date and time it was first definitively identified. For S2025U1, this epoch was set as February 2025. This timestamp is vital for future astronomers who will want to track the moon's orbital decay or changes in its brightness. It marks the moment humanity's map of the solar system officially expanded, a data point that will be cited in textbooks for decades to come. The team also measured the moon's eccentricity, how oval-shaped its orbit is. A perfectly circular orbit eccentricity of 0 is rare. S2025U1 was found to have a very low eccentricity of about 0.001. This near circle is a sign of a very mature, settled orbit. It suggests that any chaos in the moon's early history has been smoothed out by millions of years of tidal interactions with Uranus, further verifying its status as an ancient, permanent satellite. During verification, scientists hypothesized that S2025U1 might be a shepherd for the Epsilon ring. To verify this, they looked for scalloped edges in the ring particles near the moon's orbit. Webb's images showed subtle gravitational wakes in the ring dust that aligned perfectly with the new moon's position. This physical interaction with the ring system provided the ultimate real-world proof that the moon exists and is actively interacting with its environment. The final step of verification is the movement from a single research paper to a global scientific consensus. As other teams around the world, from the European Space Agency (ESA) to the Canadian Space Agency (CSA), reviewed the data, the discovery was integrated into the planetary databases used by NASA's Jet Propulsion Laboratory (JPL). This ensures that any future mission to Uranus, such as a proposed atmospheric probe, will have the coordinates of this moon preloaded into its navigation software. The verification of S2025U1 is a testament to the fact that in modern science, seeing is not believing, calculating is believing. It took months of data scrubbing, orbital modeling, and international peer review to turn a few pixels of light into a confirmed world. This process ensures that when we say Uranus has a new moon, we are speaking with the full authority of the laws of physics. The hunt for S2025 U1 is over, but its story as a confirmed member of our solar system is just beginning. When discussing the newly discovered moon S2025 U1, the first characteristic that captures the imagination is its incredibly small size. Based on initial brightness readings from the James Webb Space Telescope, astronomers have estimated the moon's diameter to be roughly 10 kilometers, or approximately 6 miles. To put this in a terrestrial perspective, the entire moon could fit comfortably within the city limits of a mid-sized metropolitan area. Its surface area is so limited that its gravity is practically negligible, meaning an average person could likely jump into space from its surface with a simple leap. The estimate of a 10 diameter is not a direct measurement, but a calculation based on albedo, or how much light the surface reflects. Because we cannot see the physical disk of S2025 U1 only, a tiny pinprick of infrared light, scientists must assume its reflectivity is similar to its neighbors, like Ophelia and Bianca. If the moon is darker than we expect, it could be larger than 10 kilometers. If it is unusually bright or icy, it could be even smaller. This uncertainty principle is a constant factor in the study of small, distant celestial bodies. Physically, S2025 U1 is unlikely to be a solid, monolithic rock. Most moons of this size in the outer solar system are what scientists call rubble piles. These are loose collections of boulders, gravel, and dust that are held together by their own extremely weak gravity. This structure is often the result of millions of years of cosmic collisions. The moon is effectively a survivor, a reaccreted clump of debris from a much larger body that was shattered during the early, chaotic days of the solar system's formation. At only 10 kilometers in diameter, S2025 U1 lacks the mass necessary to achieve hydrostatic equilibrium, the state where gravity is strong enough to pull a body into a perfect sphere. Instead, this moon is almost certainly an irregular, elongated shape, often described by astronomers as a cosmic potato. This irregularity means that its gravity is lumpy and uneven, and if we were to stand on its surface, the down direction might shift depending on where you were standing on its jagged terrain. What would the surface of this new moon actually look like? Based on spectroscopic data from the Webb telescope, the surface of S2025 U1 is likely coated in a thick layer of space-weathered material. This includes carbon-rich compounds and complex organics known as thought. Over billions of years, radiation from the sun and the magnetosphere of Uranus has cooked the surface ices, turning what might have once been a bright, white object into a dark, reddish-black world that reflects only a tiny fraction of the light that hits it. It is important to clarify that S2025 U1 has no atmosphere whatsoever. Its gravity is far too weak to hold onto even the heaviest gases. Any molecules of methane or nitrogen that might outgas from its interior would be immediately swept away into space by the solar wind. Consequently, the surface is a total vacuum, exposed to the harsh radiation of the outer solar system. This lack of an atmosphere means the temperature swings are extreme, moving from a frigid sunlit state to an even colder shadowed state in a matter of minutes. The thermal environment of S2025 U1 is among the coldest in the known universe, located nearly 20 times further from the sun than Earth. The moon exists in a permanent deep freeze, with surface temperatures estimated to be around 370 degrees Fahrenheit, 224 degrees Celsius. At these temperatures, water ice is as hard as granite, and gases like carbon dioxide and methane can exist as solid ices on the surface. This extreme cold is precisely why the James Webb Telescope's infrared eyes were so essential for its discovery. While the surface is likely dominated by rock and dark organics, the interior of S2025U1 could contain significant amounts of volatile ices. If the moon originated further out in the solar system, it might be composed of a mix of water, ice, ammonia, and frozen methane. Over time, these ices can sublimate, turn directly from solid to gas, creating tiny, temporary pits or vents on the surface. These hidden ices are the genetic code of the early solar system, preserved for billions of years in the moon's cold heart. The surface of S2025U1 is almost certainly a scarred landscape, covered in impact craters from billions of years of bombardment. Because the moon is so small, a single large impact could have been catastrophic, nearly shattering the body. Every crater on its surface tells a story of a collision with a rogue comet or a fragment from Uranus's rings. Because there is no wind, water, or volcanic activity to erase these craters, the moon acts as a permanent record of the shooting gallery. That is the outer solar system. S2025U1 sits in an interesting neighborhood, orbiting between the moons Ophelia and Bianca. Ophelia is slightly larger, at about 21 kilometers wide, while Bianca is an elongated moon, roughly 50 kilometers long. By comparing S2025U1 to these better-known satellites, scientists can begin to understand the family traits of the inner Uranian moons. All three are likely fragments of the same parent body that broke apart long ago, sharing a similar dark, icy composition. One of the most sought-after data points for S2025U1 is its density. While Webb cannot weigh the moon directly, astronomers can estimate its mass by observing its tiny gravitational effects on the nearby rings. If the moon has a very low density, less than that of water ice, it would confirm the rubble pile theory. A higher density would suggest a more rocky, solid interior. Knowing that density is key to understanding how much metal and rock versus ice and dust was present in the Uranian disk when the moon formed. New data from Webb's instrument has shown that Uranus's intermoons, including S2025U1, are surprisingly red compared to the larger outer moons. This redness is a signature of organic molecules that have been irradiated. Interestingly, this matches the color of many objects in the Kuiper belt beyond Neptune. This leads some scientists to wonder if these small inner moons might actually be captured primitive objects from the furthest reaches of the solar system, rather than local residents. Despite being water-poor, compared to the 5 major moons of Uranus, S2025U1 likely still contains a significant percentage of water ice in its bulk composition. However, this ice is often mixed with silicates, microscopic bits of rock and dust, creating a material similar to dirty snow. This mixture is what gives the moon its structural strength. In the low-gravity environment of S2025U1, this ice-rock mixture can support mountains and cliffs that would be impossible on a larger, more gravity-heavy world like Earth. On S2025U1, the concept of geology is very different. Without significant gravity, there are no landslides in the traditional sense. Instead, loose dust and regolith might slowly flow across the surface due to electrostatic charges or the tiny vibrations of distant impacts. This creates a soft, pulverized surface layer that scientists call regolith. If a spacecraft were to land on S2025U1, it might find itself sinking into a deep layer of fine, salt-like dust that has accumulated over billions of years. Every object in space has a spectral signature, a unique way. It reflects different wavelengths of light. Webb's discovery of S2025U1 was aided by the fact that the moon has a distinct infrared fingerprint. By analyzing this light, scientists can identify specific molecules, like carbon dioxide, or even simple amino acids. While the data is still being processed, initial readings suggest a surface that is chemically primitive, containing the basic building blocks that were present at the very beginning of our solar system. Uranus has a highly unusual, lopsided magnetic field that is tilted at 60 degrees from its axis. S-2025 U1 orbits right through the heart of this magnetosphere. As the moon travels, it is constantly bombarded by trapped electrons and protons. This ion bombardment changes the chemistry of the surface ices, a process called radiolysis. Over millions of years, this radiation can actually break apart water molecules, leaving behind a residue of oxygen and hydrogen that could create a microscopic exosphere around the moon. Unlike larger moons, like Ariel or Enceladus, S-2025 U1 is far too small to have any internal heat source. It has no radioactive core to speak of, and it is too small for tidal heating, the process where a planet's gravity squeezes a moon to create heat to be effective. This means the moon is geologically dead. It has no volcanoes, no geysers, and no moving tectonic plates. It is a world in stasis. A perfect snapshot of a moment in time from billions of years ago. One of the reasons S-2025 U1 is so significant is that it represents a class of stealth objects that are likely common in the outer solar system. Because it is so dark and so small, it is nearly impossible to see with traditional methods. Its physical nature is optimized for hiding. Its dark surface absorbs the little light it receives, and its small size makes it a needle in a cosmic haystack. Discovering it has forced astronomers to reconsider how many other stealth moons might be orbiting the other giant planets. There is a fascinating possibility that S-2025 U1 might have its own mini-ring or a dust halo. When micrometeoroids hit the surface of the moon, they kick up clouds of dust. Because the gravity is so low, this dust can stay in orbit around the moon for a long time before falling back or being swept away. This would mean that S-2025 U1 is not just a lone rock, but the center of its own tiny, dusty ecosystem, constantly exchanging material with the surrounding space. The discovery of S-2025 U1 is not merely a statistical addition to the satellite count of Uranus. It represents a fundamental shift in our perception of how ice giant systems are structured. For decades, the gap between the inner ring moons and the large spherical satellites was viewed as a relatively clean space, governed by simple gravitational rules. However, the presence of this new 10-kilometer world suggests that the Uranian system is far more crowded and dynamic than previously modeled. It challenges the assumption that we had already identified all significant members of the system, forcing a reevaluation of the orbital dynamics that define this distant region of space. From a scientific perspective, the most profound implication of this discovery lies in what it reveals about planetary formation and the migration of objects in the early solar system. If S-2025 U1 is indeed a captured object, as its irregular characteristics might suggest, it serves as a tether to the Kuiper belt. It suggests that the process of gravitational capture was much more frequent and efficient than previously thought. This allows researchers to use Uranus as a giant gravity trap to study the primordial materials of the outer solar system without having to travel billions of miles further into the dark reaches of interstellar space. The presence of this moon also forces a reconsideration of the late heavy bombardment theory within the Uranian system. Because S-2025 U1 is so small and sits in a stable orbit, it may be a survivor of a much more violent era. Scientists are now investigating whether this moon is a primary body or a secondary fragment. If it is a fragment, it implies that larger moons were once shattered by massive impacts, and the resulting debris reaccreted into the small, dark satellites we see today. This collision and reaccretion model is a vital part of understanding the life cycles of planetary systems. Furthermore, this discovery impacts our understanding of resonance and orbital stability. In a system as packed as Uranus's moons exert constant gravitational pulls on one another, S2025 U1 likely exists in a delicate mathematical balance with its neighbors, Ophelia and Bianca. Scientists use unbodied simulations to project these orbits millions of years into the future. Finding a new moon means every single one of those simulations must be rerun, as even a tiny mass can provide the subtle tug that prevents orbital chaos within the inner ring system. The discovery also highlights the importance of small body science. For a long time, the focus of astronomy was on the big objects, planets, and large moons. However, small moons like S2025 U1 are often more representative of the solar system's true population. They are the dark matter of our local neighborhood. By studying these smaller satellites, we get a better statistical understanding of the mass distribution in the outer solar system, which in turn helps us understand the formation of mini-Neptunes around other stars in our galaxy. In the context of the Uranian rings, the significance of S2025 U1 is transformative. Rings are not static structures. They are fluid, changing environments. The discovery of a moon so close to the ring edges suggests it may be a shepherd, a gravitational guardian that prevents ring particles from drifting away. This find could explain why certain rings around Uranus remain so sharp and well-defined despite the chaotic forces acting upon them. It turns our focus from the rings as dust to the rings as a managed system governed by these hidden tiny moons. Moreover, the find serves as a critical test for our current observational technology. Before the James Webb Space Telescope, JWST, we were essentially looking at Uranus through a foggy window. This discovery confirms that our models of the completeness of our solar system were premature. It raises the provocative question: if Uranus has hidden moons, what about Neptune? What about the asteroid belt? It recalibrates the discovery floor for the entire astronomical community, proving that even with our best technology, we are still only seeing a fraction of what is out there. There is also a chemical significance to this discovery. If S2025 U1 is found to contain high levels of specific organics, or ices, it would act as a chemical marker for the region of space where it formed. By comparing its spectral signature to the other 28 moons, we can create a family tree of the Uranian system. This allows us to distinguish which moons are native formed from the planet's original disk, and which are immigrants captured from the Kuiper belt. This chemical mapping is essential for reconstructing the history of the giant planets. The discovery also reinvigorates the debate over planetary protection and future mission safety. As space agencies plan the next generation of probes to the ice giants, the presence of small, undetected moons is a legitimate hazard. A spacecraft traveling at several miles per second cannot afford to hit even a small pebble, let alone a 10-kilometer moon. Mapping these objects now ensures that future explorers have a clear path and can avoid the gravitational mines that might be lurking in the dark. From a pedagogical standpoint, S2025 U1 is a powerful tool for teaching the public about the evolving nature of science. It demonstrates that the solar system is not a finished map found in an old textbook, but a living, breathing frontier. For a new generation of scientists, this discovery is proof that there are still worlds left to find. It moves astronomy away from the abstract and back into the era of literal exploration, where new territory is claimed through the lens of a telescope. The discovery also carries weight in the field of astrobiology, albeit indirectly. While a frozen rock like S2025 U1 is not a candidate for life, it contains the prebiotic materials water, ice and carbon compounds that are the ingredients for life elsewhere. Understanding how these materials are distributed across the moons of giant planets helps us understand how the seeds of life are scattered throughout a solar system during its formation. Furthermore, S2025 U1 forces us to look at the interconnectedness of the solar system. The fact that Uranus can capture a moon from the deep reaches of space reminds us that the planets do not exist in isolation. They are part of a giant, interconnected web of gravity and motion. This discovery helps us visualize the highway of objects that move between the inner and outer solar system, driven by the gravitational nudges of the giant planets. The discovery also provides a unique opportunity to study space weathering on a small scale, because S2025 U1 has no atmosphere and very little gravity. Its surface is a pure record of its exposure to the space environment. By studying how its color and texture change over time, scientists can learn more about how solar radiation and micrometeoroid impacts alter the surfaces of icy bodies. This data is vital for interpreting the images we get from even more distant objects, like those in the Oort cloud. There is also a profound computational significance to this discovery. The amount of data processing required to pull S2025 U1 out of the background noise of the JWST images represents the cutting edge of signal processing. The algorithms developed for this hunt can now be applied to other datasets, potentially uncovering moons around Neptune, or even dwarf planets in the far reaches of the Kuiper belt. It is a victory for the data scientists of astronomy, just as much as for the observers. The find also shifts the focus of the Uranus flagship mission, currently being discussed by NASA. Previously, the mission's moon study goals were centered on the 5 major satellites. Now, there is a strong argument for including a small moon survey as part of the mission's primary objectives. S2025 U1 has become a high-interest target that could provide the most pristine samples of ancient solar system material, potentially making it more scientifically valuable than the larger, more geologically active moons. In the realm of celestial mechanics, S2025 U1 acts as a clock. Its orbital decay or shift over the coming decades will give scientists a precise measurement of Uranus's tidal dissipation, the way the planet's interior responds to the gravitational pull of its moons. This is a rare chance to look inside the ice giant by observing the behavior of a tiny rock on its exterior. It is a form of gravitational X-ray that reveals the internal structure of the planet itself. That the discovery also brings a sense of cosmic humility. It reminds us that Uranus, a planet 4 times the size of Earth, has been hiding a moon for the entire history of human astronomy. If we can miss an entire world in our own backyard, it reinforces how much we have yet to learn about the billions of other stars and planets in our galaxy. It keeps the wonder of astronomy alive by proving that the universe is always more complex than our current models. Moreover, the find validates the massive public and private investment in the James Webb Space Telescope. When the telescope was being built, critics wondered if its focus on the deep universe would leave local science behind. This discovery proves that Webb is a universal tool, equally capable of seeing the first galaxies and the smallest moons. It provides a tangible, local return on investment that the public can easily understand and get excited about. The discovery also fosters international cooperation because the data is hosted on public servers. Researchers from around the world are contributing to the characterization of S2025 U1. It is a global discovery, where a scientist in Europe might calculate the orbit, a researcher in Asia might analyze the spectrum, and a student in America might propose the final name. This collaborative spirit is the hallmark of modern space exploration. The James Webb Space Telescope, JWST, was originally conceived as a first light machine designed to peer back over 13.5 billion years to witness the birth of the very first stars and galaxies. However, as the discovery of S-2025 U1 around Uranus demonstrates, its legacy is being fundamentally reshaped by its unexpected prowess in planetary science. This dual-purpose capability represents a monumental leap in engineering, proving that a telescope optimized for the edge of the observable universe can be equally transformative when pointed at our own cosmic backyard. 2. Appreciate the technological legacy being built here. One must understand the sheer sensitivity required to transition from deep space cosmology to local planetary observation. While galaxies are massive and bright in the infrared, a 10-kilometer moon at Uranus is a minuscule, cold speck. The fact that Webb's near-infrared camera, NIRCam, can resolve such a faint object while simultaneously observing the ancient universe is a testament to the telescope's dynamic range. This flexibility is what allows Webb to bridge the gap between macroastronomy and microastronomy, creating a unified legacy of discovery. Legacy of Webb is also defined by its unblinking eye. Unlike ground-based telescopes that must deal with the turbulence and chemical interference of Earth's atmosphere, Webb operates in the pristine vacuum of the second Lagrange point L2. This stability allows for the long-duration exposures necessary to find stealth moons, like S-2025 U1. By removing the atmospheric veil, Webb has set a new standard for what we consider clear data, effectively retiring the era of blurry, pixelated dots and replacing it with crisp, mathematically precise observations. Furthermore, Webb's legacy is inextricably linked to the success of its cold technology, because the telescope operates at temperatures below 50 Kelvin. It can detect infrared signatures that would be drowned out by the heat of any other observatory. This thermal silence is the foundation of its ability to find new moons. S-2025 U1 is essentially a heat map discovery. Its existence was confirmed because Webb could sense the microscopic amount of thermal energy it absorbed from the distant sun. This mastery of infrared physics is perhaps Webb's most enduring contribution to the field of astronomy. Webb is also rewriting the textbooks on the efficiency of space missions. In a single observation cycle, the telescope often gathers data for multiple scientific disciplines. While the primary objective of a specific observation might be Uranus's atmosphere, the bycatch, such as this new moon, proves that every minute of Webb's time is exponentially more productive than previous observations. This efficiency is creating a massive data archive that will be mined by researchers for decades, likely leading to the discovery of even more moons, long after the telescope has completed its operational life. The telescope's legacy also involves the democratization of space data. The high-resolution images of the Uranian system and its new moon are made available to the global scientific community through the Barbara A. Mikulski Archive for Space Telescopes MAST. This allows a researcher in a small university to contribute to the discovery of a new world, just as easily as a scientist at a major space agency. Webb is not just a tool for the elite. It is a global resource that is fostering a new era of international, collaborative science. In terms of engineering, Webb's legacy is one of precision, deployment. The fact that a telescope with a 6.5-meter folding mirror and a tennis sunshield could be launched and perfectly calibrated 1.5 million kilometers away is a victory for human ingenuity. Every time a new moon is found, it validates the thousands of hours of testing and the billions of dollars of investment. It proves that we can build complex, autonomous machines that can operate in the most hostile environments imaginable and still deliver results that exceed our wildest expectations. Webb is also acting as a temporal bridge between generations of astronomers, For those who grew up with the grainy images from Voyager 2, Webb represents a long-awaited homecoming to the outer planets. For the new generation of students, Webb is the standard by which all future discoveries will be measured. It provides a continuous thread of exploration, ensuring that our curiosity about the ice giants remains active during the decades-long intervals between dedicated planetary missions. The spectroscopic legacy of Webb is equally profound. By breaking down the light from objects like S2025U1, Webb's NIRCam instrument is creating a periodic table of the solar system. We are no longer just counting objects. We are understanding their chemistry. Webb's ability to detect water, CO2, and organic molecules on a 10-kilometer rock, billions of miles away is a feat of chemical analysis that was unthinkable just 20 years ago. This data is the raw material for future theories on how our solar system's chemical soup was mixed. Webb's legacy also includes its role as a risk reducer for future exploration. By mapping the Uranian system in such high detail, Webb is identifying the gravitational minefields that future orbiters must navigate. This reconnaissance legacy makes space travel safer and more efficient. Every new moon found is one less unknown variable. For the engineers who will eventually design the flight paths for the first human-made probes to orbit the ice giants in the 2030s and 2040s. The telescope is also a magnifying glass for the most common type of planet in the galaxy. As we find thousands of exoplanets, we've realized that most of them look like Uranus and Neptune. By using Webb to study our local ice giants and their moons, we are building a Rosetta Stone for understanding the rest of the universe. The discovery of S2025U1 helps us understand the orbital architecture of mini-Neptune systems around other stars, making our local discoveries relevant on a galactic scale. Webb's legacy is also felt in the field of software-driven science. The algorithms developed to subtract the light of Uranus and reveal its hidden moons are a legacy of computational excellence. These tools are now being repurposed for other fields, from medical imaging to satellite monitoring. The discovery of a moon is, at its core, a victory for signal processing, proving that our ability to see the universe is limited only by our ability to process the data we receive. The aesthetic legacy of Webb cannot be ignored. The stunning high-contrast images of Uranus's rings and its growing family of moons have inspired millions of people around the world. Webb has brought the beauty of the outer solar system into our homes and onto our screens, turning abstract scientific concepts into breathtaking visual realities. This ability to engage the public imagination is a vital part of its mission, ensuring continued support for the exploration of our universe. Webb is also a legacy of persistence. The project faced numerous delays and budget challenges over its 20-year development cycle. Its success is a reminder that great things take time, and that the pursuit of knowledge is worth the struggle. Every new discovery, including S2025U1, serves as a thank you to the thousands of people who dedicated their careers to making Webb a reality. It is a monument to the endurance of the human spirit. In the realm of cosmogony, Webb is helping us understand the end state of solar systems. By observing a mature system like Uranus, we see how moons are eventually captured, lost, or broken apart. This complements Webb's observations of protoplanetary disks around young stars, allowing us to see the beginning and the end of the planetary life cycle. This full-circle view of stellar evolution is a cornerstone of the telescope's scientific legacy. Webb is also redefining our concept of the neighborhood. By finding moons that were missed by every previous telescope, Webb is proving that our local environment is much more crowded and alive than we thought. This discovery legacy challenges us to keep looking, even in places we think we already know. It keeps the age of discovery alive, in a time when many felt the solar system had been fully mapped. The telescope's legacy is also one of multi-messenger potential. While Webb looks at infrared, other telescopes look at X-rays, or radio waves. By providing the infrared anchor for these observations, Webb allows for a holistic view of the universe. For example, if S2025 U1 were to be hit by a comet, Webb would see the thermal flash, while other telescopes would see the chemical debris cloud. This team-player legacy is essential for modern astronomy. Webb is also a pioneer of the L2 frontier. By successfully operating at the second Lagrange point, it has paved the way for future observatories like the Nancy Grace Roman Space Telescope and the Habitable Worlds Observatory. The lessons learned from Webb's thermal management and orbit maintenance are the blueprints for the next century of space-based astronomy. Its legacy is literally built into the architecture of the future. Furthermore, Webb's legacy is one of cosmic context. Every discovery it makes reminds us of our place in the universe. Finding a tiny moon around a distant ice giant may seem small, but it is a part of the grand story of how the universe organized itself from hot gas into stars, planets, and life. Webb provides the connective tissue between these different scales of existence, making the universe feel more coherent and understandable. The identification of S2025 U1 serves as a definitive starting point for a new era in outer solar system exploration, transitioning our focus from mere discovery to a phase of rigorous characterization. For decades, Uranus remained a distant, static point in our star maps. But the Webb telescope's ability to find such a small, faint object has essentially unlocked the system for researchers. Scientists are no longer content with just knowing these moons exist. The next logical step is to understand what they are made of and how they represent the broader history of the ice giants. This shift represents the natural evolution of planetary science, where a single successful observation generates 100 new questions that will define the next decade of astronomical inquiry. One of the most immediate priorities for the scientific community is the official naming of S2025 U1, a process governed by the International Astronomical Union (IAU). Following the precedent set by John Herschel in 1852, the new moon must be named after a character from the works of William Shakespeare or Alexander Pope. This tradition creates a unique bridge between the humanities and hard science, ensuring that every new addition to the Uranian family carries a literary legacy. Researchers are currently scouring plays like The Tempest, A Midsummer Night's Dream, and The Rape of the Lock for a character whose story or attributes might symbolically match the characteristics of this elusive inner-orbiting satellite. The chemical composition of S2025 U1 remains a high-priority mystery that will be addressed using Webb's near-infrared spectrograph. While early data suggests a surface rich in dark, carbonaceous material, a deeper dive into the spectrum could reveal traces of water, ice, ammonia, or even carbon dioxide. These compounds act as geological tracers, telling us exactly where in the solar nebula this moon formed. If the spectrum shows high levels of nitrogen-rich ices, it would strongly suggest that S2025 U1 is a captured traveler from the Kuiper belt, making it a local sample of the most distant reaches of our solar system. A fascinating area of future research involves the shepherding role that S2025 U1 likely plays within the Uranian ring system. Located just outside the bright Epsilon ring, this moon may exert a subtle gravitational influence that keeps ring particles from drifting away into space. By using high-resolution orbital modeling, astronomers hope to determine if this moon is the guardian responsible for the sharp, well-defined edges of Uranus's rings. If so, S2025 U1 is not just a passive rock, but an active sculptor, constantly shaping the visual architecture of the planet's surroundings. Furthermore, the discovery has reignited the conversation around the Uranus orbiter and probe UOP mission, which was recently named a top priority in the Planetary Science Decadal Survey. While the James Webb Telescope provides incredible remote data, a dedicated orbiter would be able to perform close-up flybys of S2025U1, potentially capturing images of its surface craters and jagged terrain. This synergy between space-based telescopes and future robotic explorers is the hallmark of modern NASA strategy, where Webb acts as the scout that identifies the most scientifically valuable targets for future boots-on-the-ground robotic missions. The 2025 American Geophysical Union (AGU) meeting highlighted that many of Uranus's small inner moons, including the new discovery, are surprisingly water-poor compared to the larger outer moons. This creates a fascinating compositional gradient that researchers are eager to map. Why is there such a stark difference in ice content between the inner and outer system? Future research will investigate whether the intense radiation environment near Uranus stripped the inner moons of their volatiles, or if they formed from a completely different pool of primordial material than the major moons, like Titania and Oberon. The discovery also provides a rare opportunity to study orbital chaos in real time. The inner Uranian system is notoriously crowded, and simulations suggest that many of these small moons are in unstable or semi-stable orbits. Over millions of years, they may collide or be torn apart by tidal forces. By tracking S2025U1's position over the next several years, astronomers can refine their chaos models, helping us predict the eventual fate of the entire system. This makes Uranus a living laboratory for the study of celestial mechanics and the long-term evolution of planetary systems. In addition to NASA's efforts, international space agencies are showing increased interest in the Uranian system. China's Tianwen-4 mission, currently in the planning stages for the 2040s, could potentially include a flyby of Uranus as it heads toward the outer solar system. The discovery of S2025U1 adds another waypoint for such missions, increasing the scientific return for any spacecraft that ventures into this distant territory. The global nature of this discovery involving scientists from the US, Europe, and beyond reflects the collaborative future of space exploration. Another compelling research path is the study of space weathering on the surface of S2025U1. Because the moon has no atmosphere, its surface is directly exposed to the solar wind and cosmic rays. Over eons, this bombardment creates a dark crust of complex organic molecules. Future observations will aim to determine the thickness and age of this crust, which can serve as a cosmic clock for the moon's history. Understanding how radiation alters icy surfaces is vital, not only for studying Uranus, but for interpreting data from every other airless body in the solar system. The legacy of S2025U1 will also be felt in the development of next-generation telescopes. The success of Webb in finding such a faint object has set a new benchmark for sensitivity. Engineers are already using the data from this discovery to refine the requirements for the Habitable Worlds Observatory and other future missions. If we can see a 10-kilometer moon at 2 billion miles, what else can we find? This discovery pushes the envelope of signal-to-noise processing, proving that our ability to see the universe is limited only by the sophistication of our software and sensors. Furthermore, this discovery has practical implications for the safety of future space missions. As we plan to send probes into the Uranian system, every small moon represents a potential navigational hazard. Mapping these mini-moons now ensures that future flight controllers can plot trajectories that avoid collisions or unwanted gravitational S2025U1 is effectively a newly discovered island in a sea of rings, and every island must be charted before the ships of exploration arrive. The study of S2025 U1 also provides a bridge to understanding As it turns out, ice giants like Uranus and Neptune are among the most common types of planets found around other stars. By studying the moon-andering architecture of our local ice giant, we can make more accurate predictions about the environments of the mini-Neptunes we detect light years away. Every detail we learn about S2025 helps us build a more universal theory of how these systems form and remain stable across the galaxy. The discovery also prompts a look back at the 1986 Voyager 2 data, armed with the exact coordinates and orbital path of S2025 U1. Researchers are performing data archaeology, re-examining old Voyager images to see if the moon was captured as a tiny, unrecognized smudge 40 years ago. This backward-looking research is a testament to the longevity of space data. A discovery made with the most modern telescope can breathe new life into observations made by a probe that is now billions of miles away in interstellar space. From an educational standpoint, the discovery of S2025 U1 is a powerful reminder that the map of the solar system is not a finished document. It inspires students and amateur astronomers by showing that even in our own neighborhood, there are still worlds left to discover. This spirit of the frontier is essential for attracting the next generation of STEM professionals who will be tasked with solving the even greater mysteries of the 21st century. There is also a profound philosophical legacy to this find. It reminds us that Uranus, often the subject of simple jokes, is a complex, dynamic, and mysterious world, with a family of moons that rivaled those of Jupiter or Saturn in their complexity. By humanizing the planet through these discoveries, we foster a greater public appreciation for the outer solar system. S2025 U1 is a small point of light, but it has cast a long shadow over our understanding of what it means to truly see a planet. As we move toward the 2030s, the Uranus system will likely become a primary focus for planetary science. The discovery of S2025 U1 has acted as a catalyst, shifting the ice giants from the neglected category to the must-see category. The sheer volume of papers being written about this moon's orbit, composition, and origin is a clear indicator that the scientific community is ready to dedicate significant resources to uncovering the rest of the secrets hidden in the Uranian shadows. The legacy of this discovery will also be measured in the advancement of automated discovery software. The techniques used to isolate S2025 U1 from the glare of Uranus are already being applied to other datasets, potentially revealing new moons around Neptune, or even hidden Trojans sharing orbits with the Earth. This methodological legacy means that the discovery of one moon actually facilitates the discovery of many more across the entire solar system. Finally, the find reinforces the value of long baseline science. Astronomy is a game of patience, where observations made today might not be fully understood for decades. S2025 U1 will be tracked by telescopes for the next century, providing data on how its orbit shifts due to tidal forces or the gravitational nudge of passing comets. This long-term monitoring is the only way to truly understand the life cycle of a planetary system. And it all starts with a single aha moment captured by the Webb telescope. In summary, the discovery of S2025 U1 is the opening act of a much larger scientific drama. It has established a new gold standard for planetary observation, unified the astronomical community around a new target of interest, and ensured that the legacy of the James Webb Space Telescope will be defined as much by its local discoveries as its deep space revelations. We are no longer just looking at Uranus. we are finally beginning to understand it. The journey from a nameless pixel in a 2025 image to a named, characterized, and modeled moon is a microcosm of the scientific method itself. It proves that no detail is too small to matter, and no distance is too great for human curiosity to bridge. 2025 U1 may be a tiny rock in a vast, cold system, but its discovery has set our collective imaginations on fire, illuminating a path toward a much deeper understanding of our place in the cosmos. The discovery of S2025 U1 is much more than a footnote in a celestial catalog. It is a catalyst for the next golden age of ice giant exploration. As we stand in early 2026, the scientific community is leveraging this find to advocate for a paradigm shift in how we prioritize the outer solar system. For decades, Uranus was the neglected giant. But Webb has proven that this turquoise world is a dynamic, crowded laboratory of physics. This final section explores how one tiny moon is reshaping the future of NASA's missions and our fundamental understanding of the cosmos. The timing of this discovery aligns perfectly with the current scientific roadmap. The 2023 to 2032 Planetary Science Decadal Survey recently ranked a dedicated Uranus orbiter and probe warp as the highest priority for a new NASA flagship mission. 2025 U1 provides immediate, high-value justification for this mission. While Webb can see the moon, a dedicated orbiter would be able to perform close-up flybys, mapping its surface and measuring its mass with a precision that remote telescopes simply cannot match. This new moon has effectively become target alpha for the next generation of deep space probes. As the discovery moves through the official channels of the International Astronomical Union, IAU, the cultural tradition of Uranus remains alive. Like its siblings, S2025 U1 will eventually be named after a character from the works of William Shakespeare or Alexander Pope. This naming convention does more than provide a label. It connects the cold, hard data of modern astrophysics with centuries of human storytelling, whether it is named after a spirit from the Tempest or a fairy from A Midsummer Night's Dream. This moon will forever carry the legacy of our literary history into the dark reaches of space. Scientifically, S2025 U1 is forcing a rewrite of planetary formation models, because it is so small and sits in such a stable, circular orbit. It suggests that the inner Uranian system is much older and more resilient than previously thought. Astronomers are now asking, if Uranus has 14 small inner moons, how many more are lurking just below the detection threshold? This discovery has set a new floor for our expectations, suggesting that the architecture of ice giants is far more intricate than the gas giants, like Jupiter,